Hi there, welcome back to MA 211. Today let's talk about Euler's method. Okay, and this is a numerical method for approximating the solution to a differential equation. We've spent the whole class basically talking about how, if we are given a differential equation, how can we find the solution? We want a closed form expression for the solution to the differential equation. And the truth of the matter is that even though we've spent a whole quarter doing this, there are a lot of differential equations that we cannot find a solution to. And so we'd like some method of approximating a solution. And now what do I mean by approximating a solution? I'm not going to give you a formula that is somehow close to being a solution to the differential equation. That's not what I'm going to do. What I am going to do is estimate the value of the solution at a number of different times, and hopefully my estimate of the value of the solution will be close to what the solution is. So my estimate will not be an expression. My solution, or my estimate, will be a bunch of estimates of the value of the solution at certain times. So for instance, I'll say the solution at time 1/2 is approximately 1.6, and the solution at time 2 is approximately 2.4, or something to that effect. Okay, so that's what we're going for. Okay, before we can go any farther, we really need to remember exactly what it means to be a solution to the differential equation. So for example, if you have a solution to the differential equation y prime equals negative t plus y squared, that means that every time t, y prime at t is equal to negative t plus the value of y squared at that time. So remember, there's lots and lots and lots of solutions to a differential equation, and they all go through different points. But I can tell you that if a solution to the differential equation passes through the point, say, 1, 2, right? And what's that mean? If the graph goes through the point 1, 2, that means y at time 1 equals 2, right? So here's time 1, here's the y-axis. So if your solution goes through that point, then y at time 1 equals 2, right? So if you have a solution going through the point 1, 2, then because it's a solution to the differential equation, you have to have y prime at time 1 equals negative 1 plus y at 1 squared, and that's negative 1 plus 4, and that's, well, that's 3, that's not really 2, but whatever, I'll have to remember to change that. Okay, so that means that if a solution to the ODE passes through the point 1, 2, it has to have slope 3, not slope 1. So it has to have a slope that goes about like this. Okay? So if you see a function and it's going through the point 2, 1 and it looks like that, it's not a solution to the differential equation, because its slope at the point 2, 1 is not 3. On the other hand, this function might well be. That might be a solution. And, you know, this function, that might also be a solution. But again, from the differential equation, if you know the value of the solution at a certain time, then you can calculate the derivative of the function. Okay? So same way, if you have a solution passing through the point 2, 1, then y at time 2 is equal to 1, and so y prime at time 2 has to be negative 2 plus 1 squared, and that's negative 1. Again, because you're a solution to the differential equation, and the differential equation says your derivative at the time has to be this amount. Okay? So, what's this bias? This buys us the following. Let's try and do something here. Let's take a look at this initial value problem. right? We want y prime to be negative t plus y squared, same ODE as before. And I'm telling you that the solution I'm looking for is the solution that has y at 0 equals 1/2. So it goes through the point 0, 1/2, right? Okay, so I know the value of my solution at time 0, and I know that my solution satisfies this ODE. So that means I can calculate the derivative of my function at time 0. The derivative of my solution at time 0 has to be negative 0 plus y at 0 squared. That's 1/2 squared, and that's 1/4, okay? So here's what I'm going to do. I'm going to come down. I have some blank axes. I know that my solution goes through the point 0, 1/2, and it has slope 1/4. So it's heading off like that. Okay? Now, my solution is probably not a straight line. My solution is probably, some kind of crazy curve. But what's the fundamental theorem of calculus tell us? The whole point of differential calculus is that in a little neighborhood around time 0, the tangent line approximation to my solution is a very good approximation, right? I can basically just regard my function here as a straight line with slope my tangent, right? So this line that I drew is the line with slope 1/4, and we know, let me redraw my solution. We know that in a neighborhood near time 0, this line and my function are pretty much similar. Okay? So what am I going to do? I would really like to know, say, maybe the value of my solution at time point 2, or sometime after time 0. I'm given the value of my solution at time 0. That was in the initial condition. I would like to know the value of my solution at time 1/2. Not at time 1/2, y at time point 2. I have no way of knowing that, but I know that this curve, my solution, near time 0 is pretty close to this tangent line that I drew. And I can find out the value of this tangent line at time point 2. That's no problem, right? I know that my tangent line has, let me see, my tangent line goes through the point 0, 0.5. So the value here at time point 2, I'll call this y tilde. That's my approximation to y at time point 2. Y tilde at point 2 is going to be, let's see, my solution starts at 0.5. It heads up with a slope of 1/4 for 0.2 units. So that's 1/4 times 0.2. And that is, let me see, I figured it out down here, that is 0.55. Okay, so my tangent line at time 0.2 has value 0.55, and the whole idea of differential calculus is that, well, this tangent line stays pretty close to the curve near time 0, so my curve must have value about 0.55 at time point 2. So we'll take that to be our approximation. We've now approximated, we think, my solution at time 2. Well, it's about where the tangent line to y at time 0 goes through, ends up at time point 2. So that would be y at time 0 plus the slope of the line, y prime at time 0 times the run, 0.2, and I get 0.55 there. Okay, so now let's try again. We now have an estimate of our solution at time point 2. And now maybe we want to know, well, what's our solution do after it gets to time point 2? Well, since we know about what the value of our solution at time point 2, we can calculate about what its derivative is at time point 2. Let me just grab another color here. Let's see, we'll do the same thing. We know that the value of our solution at time point 2 is about 0.55. So let's see, so y prime at time point 2 has to be about, well, we'll just plug everything into the ODE. It'll be negative time plus the value squared. So that's about 10.1025. So our solution at time point 2 has value approximately 0.55, and it has derivative approximately 0.1, so a shallower angle than before. Oops. So it's at a shallower slope than before, okay? So now that we've calculated our derivative at time point 2, now we can use that information. We know the value of y at time point 2. We know its derivative at time point 2. Now we can use that information to maybe estimate the value of y at time point 4. This distance between estimates is called the step size. So I'm just stepping along and I'm making estimates of the value of y at different times. Okay, so let's see, what could I do here? I can say, well, this value is going to be about, this tangent line starts at 0.55, so y tilde at time point 4 is going to be, I start at 0.55, this tangent line has slope 0.10 something or other, it's 1025. So I'm going to head off from 0.55 with a slope of 0.1025, and I'll take 2/10 of a step, so that's plus 0.2 times 0.1025. And that gives me my new estimate, and I wrote down what that estimate is here. It's 0.5705. Okay? And now I'll just keep doing this. Now I know the value of my solution, or approximately I know the value of the solution at time point 4. So I can calculate its derivative at time point 4. It's negative, I just plug everything into the ODE, and I get negative 0.07. So my solution starts going downhill very loosely at this point. And once I have the slope of my solution at time point 4, I can use again the tangent line approximation and get an approximate value at time point 6. And then once I have the approximate value at time point 6, I can go ahead and calculate the derivative at time point 6, and so on and so forth. And I just decided to quit. I approximated my solution out to time 1. Okay? So from this data, okay, we can go ahead and plot everything. And then if you wanted to, you could connect these with a straight line to make the graph look, sort of nicer. But anyway, this is our guess. This is what we think the solution to the initial value problem looks like. If you could find that solution and you plotted it, that's what we think it would look like. What we went through, this is called Euler's Method to approximate the solution to an initial value problem. Euler's Method is a classic method for doing this, okay? Let me see, distance. So yeah, what we're going to do is we're going to be given the value of our solution at a certain time, say at the initial value. So we want to approximate y at some time t. So for instance, I want to approximate y at time point 2, and I know the value of y at some previous time, like 0. The distance between those two times is called the step size, and we can choose that however we want. So we could take steps of point 2. So if we took steps of point 2, then we would be given y at time 0. We could estimate y at time point 2, and then y at time point 4, and then y at time point 8. Or we could use a step size 0.1, and then we'd be given y at time 0. We'd estimate y at time point 1, then estimate it at time point 2, and then at time point 3, and so on. Okay. And because the tangent line approximation is a better approximation to our solution in small intervals for small amounts of time, it's best to use small step sizes to get accurate results. Now, of course, using smaller step sizes means you'll have to do more work and calculate more things. If you want to estimate y at time 1 and you use step sizes of 0.2, then you'll only need to do 5 estimates to get y at time 0.1. If you use a step size of 0.1, you'll need to do 10 estimates, and if you use step sizes of 1/100th, you'd need to do 100 estimates to finally get your approximation to y at time 1. Okay, so this is what we do. We'll be given the value of y at a previous time, t minus h. We can calculate the derivative of y at that time. So for instance, we were given y at 0. We can calculate y prime at 0 by plugging it into the right-hand side of the ODE. This f of y and t, that just means the right-hand side of the ODE. And then we can use the tangent line approximation to say, well, y at time t is about the previous value of y plus the derivative of y at that time times the step length, h. That's exactly what we did above. And then we repeat. Okay, so let's do an example here. Let me just get ready here. I've pre-calculated some things. Okay, so we want to use step sizes of 0.1 to estimate the solution to y prime equals sine 2t sine y and y of 0 equals 1 between time 0 and time 2.5. Wow, it's not a step size of 0.1. That'd take forever. It's a step size of 0.5 that I'll use. Okay, so for this example, the right-hand side is sine 2t sine y, and we're given y at 0, and we'll use that information. We'll take a step of 0.5, so we'll estimate the solution at time 0.5. After that, we'll estimate the solution at time 1, and after that, the solution at time 1.5, and so on and so forth. So we know that y at 0 equals 1. With the knowledge of y at 0, we can calculate the derivative at time 0. That would be sine of 0 times sine of 1, and that's of course 0. So now we can calculate y at time 0.5. That's going to be about y at time 0 plus 0.5 times y prime at time 0, and that's 1 plus 0, and that's 1 again. Okay, so now I have an estimate to y at time 0.5. I can calculate the derivative at time 0.5 by plugging in time 0.5 and our estimate to y at time 0.5 into the derivative. So that would be sine of 2 times 0.5 times the sine of 1, and that is 0.7081. Okay. Now with that information, now I can estimate y at 1, right? That would be y at 1 is about y at time 0.5 plus my step size of 0.5 times the derivative, y prime at time 0.5. So let me see, my y at 0.5 is right here, my y prime at time 0.5 is right here, and if I calculate that, I get 1.3540. You can just plug this into a calculator and do it. Alright, so now I have my estimate to y at time 1. I can calculate my y prime at time 1. That would be sine of 1, sine of 2 times 1, times the sine of 1.3540, and that is 0.8880. Okay, once I have my derivative at time 1, now I can estimate y at time 1.5. Y at time 1.5 would be about y at time 1 plus my step length 0.5 times y prime at time 1. And if you calculate that, so you have all the information you need, you have y at 1 approximately, you have y prime at 1 approximately. If you calculate all that, you get 1.7980. Let's see. If you calculate y prime at time 0.5, again, you just plug in 1.5 and y of 1.5 into the ODE, and you'll get sine of 3 times sine of 1.7980, and that is, let me look, 0.1375. Once you have the derivative, again, now you can calculate y at time 2. That's y at 1.5 plus 0.5 times y prime 1.5. If you calculate that, that's 1.8668. Now you calculate y prime at time 2, and if you just do it, you'll get negative 0.7239, and then you can calculate y at time, the approximation to y at time 2.5 is y at time 2 plus 0.5 times y prime at time 2, and if you do that, you get 1.5048. Alright, so I've plotted those results. Here we actually have the true solution. You can actually solve that ODE. It's separable. It's sort of messy, but you can do it. So that's the true solution, and here I've plotted the approximation using Euler's method. And you see, well, no, it's not exactly right on, but it's not terrible either. That's, it gets the general behavior of our solution about right. And if we wanted, we could use a lot smaller step sizes, and hopefully we'd get a lot better approximation to our solution. So I did that here. Here I used step sizes of like 1/100th or something like that. And you can see, yeah, the true solution and the approximation are pretty darn close there. So if you use Euler's method with very small step sizes, yeah, you end up doing reasonably well. Okay? So really, that's it. Can you use Euler's method to approximate a solution to the differential equation? And I think you can.